Yes. So for our last 8 minutes or 7 minutes, we'll explain how this machinery on diffeology, this tangent structure on a subcategory of diffeological spaces, can give us the algebras of diffeomorphism groups, which, as we saw, are naturally themselves diffeological. So how do we do this? Well, we're going to begin by explaining better. Oh, sure. Yeah, so while Christian is erasing for me, I'll give you a verbal preview. We have this tangent functor. It's some con extension, some co-limit. When I first saw this, I didn't know what this meant, and I had no sense of what kind of things I was getting when I took tangent functors. For groups, or more generally for mapping spaces, we can have a nice little diagram that will say what is T of map Mn, for instance. So we have the following diagram, which is the basis of our work here. So, well, it's kinematic for one. The T is kinematic. So let's say I'm going to use self maps because we want to talk about diffeomorphisms, so maps from M to M. Of course, you could put N here if you like. This will give us the tangent bundle here by differentiating at time 0. So paths into mapping spaces, these go by another name, homotopies. So we take a homotopy, we take its time 0 derivative, and that's how we get our T. It's a quotient of path space. Now, how do we understand T? Well, if we have a homotopy phi in here, or phi, then we can do the following. We can assign mu into, this will be mapped into Tm. So mu phi, I need to say what it does on an element of the manifold. I'll differentiate it, but x will be fixed now. So it's d by dt phi t of x. I'll put the t argument in the subscript here. Okay. So on the one hand, I have this abstract quotient, which is how I get my diffeological tangent bundle. This is true even without mapping spaces. And on the other hand, I have a very concrete way to associate to a homotopy a vector field. And when I say that this helps us understand the tangent bundle, what I mean is that there exists a unique smooth map, nu, connecting these. And because this is a quotient, I don't need to really say what nu is on elements, right? The universal property of quotients, as long as you check that mu is constant on the del fibers, we get this nu. And nu is smooth automatically because of diffeological reasons for quotient maps. But moreover, what Christian showed, and what sort of was, I say, the genesis of this project, and it's a lot of hard work, is that, so Christian, so B24 maybe, I don't know exactly why, is that nu is an isomorphism in diffeological spaces. Yeah.
No, exactly that. What is in this category an isomorphism?
What is an isomorphism?
I mean, just preserving the actions, but you have in mind some example.
Any diffeomorphism of manifolds are isomorphisms?
Well, but you just said we shouldn't think of these objects as manifolds, so...
Yeah. So this is an isomorphism of two spaces, but neither of these spaces is locally isomorphic to anything.
The condition is it maps smooth paths to smooth paths. And the inverse does the same. It's easy to check.
And it does correspond to a certain distinction between topological spaces. For instance, two spaces which are not topologically equivalent can have the same diffeology.
Yes. So think of diffeology as sort of divorced from topology. Diffeological structures can exist completely independently of having any topological idea on X.
Even on groups.
Even on groups. Yeah, and in fact,
The real line and the circumference are the same group.
yeah, so in fact, I mean, a diffeological group might not have an underlying topological group, for instance.
Sorry, the real line and the S1 is different.
So maybe I have, I'll take 3 minutes, I'll finish the story, and then we can discuss this.
This identification is very well known in variational calculus. So even in on M is N, so the tangent space or tangent variations are maps into the Pullman bundle. Yeah? So this is absolutely standard in variational calculus.
Yes, but I think that the non-standard thing that enters here is
However, you don't put any infinite dimensional.
Yeah, so I'm going to, there's 2 minutes. Okay, so this has been done, and it's Christian. And the idea is sort of you want to show that this mu is surjective, and then also that it's that this is mu is injective. So some things that happen, for instance, are given some vector field V on M, say a vector field, maybe I'm looking at things over the identity, so a vector field. Given a vector field V on M, find some phi such that it generates V at time 0. Find a homotopy that generates a vector field. And for mapping spaces, you just need homotopies, there's no diffeomorphisms, and you have some flexibility. But now, if I do a trick, which is, I'm sorry, always annoying if you're trying to write things down, but we're running out of time. But I shouldn't have erased that one. I'll put it back. If we put diff here, this is now we're going into open things. For M non-compact, then this quest to show, for instance, surjectivity of mu, to show that mu is an isomorphism, has a much stronger question. Find a isotopy, so a homotopy through diffeomorphisms that gives V. And you might say, well, the flow. But the flow is not going to be defined on all of M necessarily. So you need to get much more creative to construct such isotopy. And one of the results is that we have shown that you have one. To me, it was not clear that such isotopy exists. And I mean, if someone had a literature reference, we'd be happy to know that someone did this. But I have not found it. We have not. I say I have not found it. Also, injectivity of mu is sort of very subtle, but I don't think I have time to speak about this. And my last sentence will be, this thing has a natural Lie algebra structure when you take the identity as your base point. TE of diff has a Lie algebra structure coming from this tangent structure, Rosicky axioms, etc. Vector fields also have a Lie algebra structure, which we know. But is it clear that they're the same? I would say perhaps not. You need an argument to say that this abstract Lie algebra structure that came from this tangent structure machinery is the regular, usual, friendly one on vector fields. And that's another result, is that they are the same. And I think that will be it.